and I'll be talking to you about post-quantum cryptography from lattices. So like one disclaimer, like I'm gonna mention quantum computing like once or twice in this entire talk. Like basically what I mean by post-quantum here is that this is somehow cryptography that doesn't care about quantum computers. So I'm sort of not going to care about them that much. But if you're into quantum computing, like this is still relevant to you, I think. Also, I'll mostly be talking about other people's work, but a little bit of the work I'll be talking about is joint work with Devesh, who just spoke, and Huck, Sasha, and my supervisor at MIT, Vinod. So with those disclaimers out of the way, let's begin. So first, I want to tell you about public key encryption. Just very basic stuff. So we need encryption in this world. And we need encryption for the following reason. This is a problem that I have a lot. So I have some embarrassing personal email that I need to send to somebody, right? And in order to send it to somebody, I have a Gmail account, and I need to get my embarrassing personal email to Gmail, and then presumably Gmail gets it onto forwards it onto the recipient. But let's just worry about me getting it to Gmail. This is like one thing to imagine is that like there's sort of a wire that comes out of my laptop and goes through the Pacific Ocean and comes out in the Bay Area and travels south a little bit and goes to Mountain View and like plugs into one of Google's servers, right? And if that were actually the case, then this would be a very easy problem. But in reality, what happens is I send it through the internet, right? And the internet's full of shady characters like this guy, who would like to read my embarrassing personal email and maybe, publish it online or something like this. So we need some way to, if this were to happen, I'd be very sad, and we need some way to mitigate this, to somehow get my message to Gmail without some shady character like this guy reading it. And one method for this, sort of the simplest method, is what's known as secret key encryption. And secret key encryption, as the name suggests, Google and I share a secret key. So we each have this secret key, which I'll call K. Think of it as like a random string of zeros and ones. And then I'll encode my message, say, as a bit string itself. Turns out it only takes 4 bits to embarrass me. And then maybe my key is also 4 bits, and I can do like the most naive thing ever, which is I can take the XOR. So my ciphertext can be, in each bit, I put a 1 if the 2 bits are different here, and a 0 if the 2 bits are the same. And so if I do this, then when I send my message through the adversary to Gmail, what the adversary sees is just this ciphertext, which to him is uniformly random. It's nonsense. He doesn't learn anything about my message. But Google can decrypt, right? In fact, this operation is an involution, so Google can just do the same thing again and get my message back. This is secret key encryption, and this is just to symbolize that the adversary can't read my message. But there's a really big problem with secret key encryption. I should say, I know that you guys have seen this before. I'm trying to give a different perspective. There's a really big problem with secret key encryption, which is the secret key, right? So the question is, where does it come from? And in particular, how do I share a secret with Google? Right? I mean, the most natural answer is, I'll just send it to them over the internet. But that, sort of becomes a little circular. So we have to figure out some way. And I think it's kind of interesting to imagine a world in which this is actually what the best we had. Right? Like you can imagine a world in which, like, Google sends you a secret key in the mail or something, or you go to the secret key store, some trusted third party, and you say, okay, I want a Google key, and they give it to you, or maybe you just like physically walk to Mountain View, and they give you a piece of paper that has your secret key on it. Like this is a very plausible world, I think, but luckily we don't live in that world because we have what's known as public key encryption. And I think if you've seen public key encryption, if you've known about it for decades, then you forget that it's complete magic. Like the fact that public key encryption exists is completely ridiculous. It's just we've all gotten used to it, or many of us have gotten used to it. Of course, we've known about it since the 70s. It was an idea due to Merkle and Diffie and Hellman. And in public key encryption, the scenario is slightly different, right? Gmail has this secret key. I have this public key. And I have some magical encryption algorithm that lets me, just using the public key, encrypt my message, turn it into a ciphertext. And when I send it to Google, to Gmail, Gmail has some magical algorithm now using the secret key that allows Google to decrypt. And I mean, sometimes this is called asymmetric encryption, the asymmetry being that I use the public key and Google uses the secret key. And when I say public key, I really mean public. So in particular, like this bad shady character over here has the access to the public key, right? But the magic of public key encryption is that somehow, even though the adversary knows everything that I know, I'm somehow able to pass a secret to Google without the adversary being able to read it. And you know, again, we're all jaded at this point, I think. Most of us are jaded, but this really is quite magical. The fact that this is possible, I think, is really quite surprising. Should still surprise us. And this is important. So we don't just use it for communicating with Gmail. We use it to you know, do online transactions and to communicate with our friends, or sort of more importantly, political dissidents in authoritarian regimes use this to communicate. We also use this to, you know, transmit personal health records and things like this. But actually listing examples is kind of silly because more than half of all internet traffic uses this. It's a protocol known as TLS, or used to be called SSL. So more than half of all internet traffic is secured using public key encryption. So this is, you know, big deal. We're talking trillions of messages. Actually, it's probably an underestimate. I don't actually know. But there's one drawback of public key encryption, which is that the security of the scheme depends on some computational hardness assumption. So in other words, when I said before that the adversary can't read my message, I don't mean that if the adversary had infinite time, he couldn't figure out what my message was. I mean that there's some computational problem that the adversary would have to solve, and maybe if I set my parameters right, then even if the adversary had a computer, say the size of the Earth, and he ran it until the heat death of the universe, he still wouldn't find my message. You know, so like, it's doable, just not in practice. That's the kind of guarantee that we want out of these things. And part of the reason that I'm stressing that this is magical is because there are very few ways that we know how to make this work. Like secret key encryption, like a random function essentially gives you secret key encryption. So in other words, like throw spaghetti at a wall, interpret it as Python code, and you'll get a secret key encryption scheme. But public key encryption, we only know a couple different ways to do it. One of these ways, which probably most of you have heard of, is what's known as factoring-based encryption, in particular RSA, due to Ravesh, Shamir, and Edelman. And here, I won't tell you the whole scheme because it's rather complicated, but the reason we call it factoring is because the secret key is two primes, P and Q, and the public key is their product. So these are two large primes, and this scheme, without even telling you anything else about it, certainly this scheme can't be secure if factoring were easy. Right? If given P times Q, I could find P and Q, then I could find the secret key given the public key, and we can't have a secure public key encryption scheme. So that's the computational assumption that we use here. Another one, which is kind of less well known, but actually what's really used in practice now, is what's known as Diffie-Hellman discrete log-based constructions. Here the secret key is some number x, and the public key is some group element, and the group element raised to the power x. If you don't know what that means, it's completely unimportant for this talk. And again, these are the two things that we use. So when I say half of all internet traffic uses public key encryption, I mean half of all internet traffic uses this. So half of all internet traffic is meant to be private, but it's only private if one of these two problems is hard. And they're actually very similar problems. Basically, every way we know how to break one, we know how to break the other the same. There do exist other constructions. That's why I'm here. In particular, there exist lattice-based constructions. I'm just going to sort of sweep that under the rug for now. These are due to my advisor, Oded Regev, in 2005. So this came much, much later. But I'm not going to say anything about that. And just in case there's someone in the audience who knows of something else, I'm going to say there exist other constructions. But they're much, much less studied than the first three. So morally, well, OK. I won't say any more in case there's someone in the audience. But we live in this magical world in which we have public key encryption, and that's really convenient, right? Otherwise, we'd have to walk to the secret key store every day or something. But we live in a world also where this horrible coincidence happened, right? Nearly half of all internet, or more than half of all internet traffic is secure under the assumption that factoring or discrete log are hard, and a quantum computer can efficiently factor and take discrete logarithms. This is a result due to Shor in 1994. I assume most of you have heard of it already, but I want to emphasize how incredibly unlucky we got. Right? I mean, quantum computers are extremely useful, but the list of problems for which we know an exponential gap between the running time of classical computers and quantum computers is really short. I mean, I can name 3. There are probably more than that, but 2 of the 3 are these, and the other one is simulating quantum systems. So like, we're in this incredibly unfortunate world where 2 of like sort of the applications of quantum computers aren't applications, they're like negative applications, right? Nobody wants to factor, right? Like it's not like, I mean, it's like a toy. It's a toy problem. I give you some gigantic number and ask you to factor it. Like there aren't applications of that, but there are negative applications in the sense that if you can factor and you're not a very nice person, you can read everyone's private messages on the internet, which is really quite unfortunate. So we got really unlucky. But we can't just sit around and cry about it all day, or at least I finished doing that yesterday. So now we need a new way to secure communications. You like my jokes. And I want to emphasize that we're already late. What I mean by this is, I mean, we learned this from Edward Snowden, but probably we knew this already. Governments and other agencies are sucking up basically all internet traffic, or at least all internet traffic they think might be interesting to them, with the intention of decrypting it later if they find a way to decrypt it later. One way that they could find to decrypt it later would be to factor or to get a quantum computer, right? So if we build a quantum computer in 10 years, the messages that we're sending today will be read by somebody. Including rather nefarious people. If you think the NSA is good, then you probably don't think Russian intelligence services are good or something like that. So we're really, really late to this. And so we should have done this yesterday, but we didn't. We need a new way to secure communication. How are we going to do it? With lattices. So a lattice is a discrete set of vectors in n-dimensional space. I'll be drawing 2-dimensional space for you today, but picture n-dimensional space if you can. Think of n as 1,000. And the lattice is specified by a basis, b1 through bn, of linearly independent vectors. So really a lattice is like a discrete analog of a vector space, right? So a vector space is also specified by a basis of linearly independent vectors. The difference is, so here's a basis for this lattice, and the difference is that the lattice is the set of integer linear combinations of the basis vectors, as opposed to, say, real linear combinations of the basis vectors, right? So in other words, I take these basis vectors and I add and subtract as much as I want, but I never multiply by square root 2 or a half or anything like that. And they have this nice, pretty structure, right? I mean, these things arise in physics and crystallography and things like this, and they're very pretty geometric objects in high-dimensional space. I wrote a thesis about it. Just to make sure we're all on the same page, let's notice that this is in fact a lattice point. It's a lattice point because it is 2b1 plus b2. And one thing that's interesting about lattices that's going to be very relevant for us is that the basis of the lattice is not unique. Maybe an analogy with vector spaces. For example, here's another basis for the same lattice. You can check that it's a basis just by seeing that this point and this point, my old basis, is expressible as integer linear combinations in my new basis. And maybe you can see that by staring for a second. And there's kind of a notion of good bases and bad bases in the sense that it's nice to have a basis consisting of short vectors, right? I mean, this is ugly. We'll see why we don't like it later, but morally, this is a rather ugly basis. You can see the geometry of the lattice much better if I give you these 2 vectors than if I give you these 2 vectors. And finding a good basis, finding short vectors in a lattice, we think is a hard problem. Not in 2 dimensions, but in n dimensions. And in fact, we can make that more formal. So we have a computational problem called the shortest vector problem, or the gamma shortest vector problem, where gamma is this parameter that's an approximation factor larger than 1. It's defined in terms of these things called the shortest non-zero vectors, which are the shortest vectors, say, in Euclidean norm. So 0 is the shortest vector in the lattice. This is annoying. The non-zero shortest vector is interesting. And we can relax this notion by defining gamma approximate shortest vector. So a gamma approximate shortest vector is a vector whose length is at most gamma times the minimal length of a non-zero vector. With this, we can define a computational problem. So we call it the shortest vector problem, or SVP is just the problem of finding shortest non-zero vector in the lattice. So finding a guy like this, assuming I drew this right. And gamma SVP is the approximation version. So I don't need to find a shortest vector, I just need to find a gamma approximate shortest vector. So I can be off by a factor gamma. And here's a slide that you shouldn't look at very carefully. But I just wanted to show you, mostly I made this slide and I'm annoyed and I want to torture people with it, but I just want to show you there's been lots of research on this problem, right? This is a very, very well-studied problem, and sort of for the whole spectrum of gammas, this problem is interesting and quite well-studied. But all you need to know for this talk is that the fastest known algorithms run in exponential time, 2 to the some constant times n. The constant won't be important. That's a result of a long series of works where we've improved the constant over and over and over again. And this is true for the approximation factors relevant in this talk. I'm going to be very informal about the numbers going on, but this is what's relevant for us. Okay? Okay. So now I'm actually going to show you a public key encryption scheme. So these things are magical, and like describing RSA, like you can't describe RSA to a man on the street. I think you can almost do this for lattice-based cryptography. It's really quite simple. So I have some lattice, and Google, Gmail, has a nice basis for the lattice. You can imagine that like Google just sampled these 2 vectors randomly from a ball or something, so they're guaranteed to be short, and then considered the lattice generated by them. So it's not so hard to generate a lattice together with a nice basis for it. So that's the secret key. The public key is going to be a bad basis for the lattice. So you can see it's so bad it doesn't even fit. And then in order to send my embarrassing personal email to Gmail, what I do is I encode it as a lattice point, say this lattice point. So this is analogous to how before I encoded my email as a bit string. Now I'm encoding it as a lattice point, which means, so I have this basis, it has integer coordinates in this basis, so it means it's a list of n integers. You can imagine a way of going from long strings like emails to lists of n integers. So if I were to send this lattice point, that would not be secure, because anyone with the public key could figure out the coordinates of this lattice point in my basis, and they'd find my email, my embarrassing personal email. But what I do instead is I just add a little bit of noise. So instead of sending the point itself, I add some other point in real space that's not in the lattice that's very close to the right answer. And the idea here is that anyone with a public key can do this. So this is a public key encryption scheme. All I needed was the public key to create the message. And Google, Gmail, can decode this message. How? Well, depending on the parameters, there are more clever things that you can do. But one thing you can do is you can write this point in the coordinates of this basis, just with linear algebra, which is efficient. And then you can round the coordinates, right? And because I chose this point to be so close to a lattice point, its coordinates will be nearly integers. And when you round, you'll get back to the lattice point. Does that make sense? So this is a very simple public key encryption scheme. We think that it's secure. So we think that an adversary, I mean, I didn't define parameters at all, but if you parameterize this properly, we think that an adversary would need 2 to the cn time to decode this message. I should say, don't implement it this. This is a caricature of what you really do. But implemented properly, we think that this is 2 to the cn hard to break, which is really quite good, right? Google, we can encrypt and decrypt in like, I don't know, n squared time or something, and adversary takes 2 to the cn time to break this. So this idea turns out to be extremely powerful for some reasons that I'm really not going to discuss in this talk. For example, we know how to build really cool cryptographic primitives. So I'm blown away by public key cryptography. Like, to me, that's magic. But there's far more magical things that cryptographers now know how to do thanks to lattice-based cryptography. You might have heard of fully homomorphic encryption, which is this thing where you can do computation on the ciphertext without knowing what's in the ciphertext. It's really cool. due to correct gentry. And there are other things like functional encryption, homomorphic signatures, and IB and AB, all these crazy things. Like this has been a real revolution for cryptographers. But I'm not going to talk about that. Also, this is a very well-studied problem, and I'm going to say a lot more about that later, but lattice-based crypto is quite well-studied. But for the purposes of this talk, the most important thing about lattice-based crypto, well, the second most important thing about lattice-based crypto is that it's apparently secure against quantum computers, right? So there's no analog of Shor's algorithm here. Shor's algorithm can factor, it can solve discrete log. We don't know how to break lattice-based crypto using quantum computers. So that's good. And because of this is about to be used by a lot of people. In particular, like we're basically planning, as I understand it, to move the internet over to this, to lattice-based crypto instead of factoring-based and discrete log-based crypto. For example, I mean, the way that this is happening formally is there's this governing body called NIST. It's a US governing organization, National Institute of Standards and Technology, and they put out standards of encryption schemes and lots of other things. And they're sort of the de facto people who choose what cryptography gets used on the internet. And they're currently having a competition, don't read this, they're currently having a competition to standardize post-quantum cryptography, by which it's going to be lattices that win. Like almost all the submissions are lattices. I'm not sure if there are any non-lattices left. Yeah, and you know, they gotten lots of submissions. This is just a small subset that have cool logos. They have cool names like Crystals and A New Hope and Frodo and Falcon and all this cool stuff. And meanwhile, there's sort of this parallel thing going on where in the private sector, people are implementing and testing this stuff. Like Google has tested lattice-based crypto at scale in its Chrome browser. So the point is that lattice crypto is coming. How soon? I mean, we should have done this yesterday because, again, you know, every year that we're not doing this, adversaries are collecting messages, and if we have a quantum computer, they're going to go back and read them. I don't really know how quickly this is going to happen. People tell me 5 years. Whether that's true or not, I don't know. So we're going to use this. How secure is it? Is everyone okay? Okay. Skeptical. So one thing that you should know about computer scientists is we don't know how to prove the security of any cryptographic scheme formally. In fact, we don't even know how to prove that any computational problem is hard. This is a really big problem in computer science. We haven't cracked that nut. We can't prove lower bounds. So I'm not going to show you a proof that lattice-based cryptography is hard. I'm going to show you evidence that breaking lattice-based cryptography is hard. That's the best we can do. So first piece of evidence, nobody's broken it yet. Right? And some number of people have tried to break it. So other people give talks in which they say many people. I'm not sure that that's really justified. But I know a lot of smart people, or I know some smart people who have tried to break it. So that's some evidence. And, you know, I'm kind of telling a joke, but if I were giving a talk about Diffie-Hellman or RSA, the talk would end here. This is usually more or less the only evidence that we have for the security of a crypto scheme. Well, we tried to break it, we failed. I'm exaggerating a little, but not much. For lattices, we have more evidence, which is cool. And to tell you the evidence, I first need to tell you like a technique that we have for arguing about hardness of problems. It's a reduction. So what we like to do, we take some computational problem, problem A, and we reduce it to some other computational problem, problem B. We say that A reduces to B. And what that means is I prove that if B can be solved efficiently, then I can solve A efficiently. In other words, if someone comes up to me and hands me this black box where I can feed it in instances of problem B and it gives me out the answer, and I can use that to solve problem A. Does that make sense? Okay. And so this direction, if we can solve B efficiently, then we can solve A efficiently is interesting. But the more interesting direction is the contrapositive, right? If A is hard, then B is hard, right? And so usually instead of arguing about hardness directly, which we really don't know how to do, we conjecture that some problem A is hard, and we prove that it reduces to problem B, and that gives us strong evidence that problem B is hard. So that's what we do for lattice-based cryptography, or that's what I'm going to show you some results like that. And these results are all going to have to do with that problem gamma SVP that I defined before, right? So it's this problem of finding short vectors, and it has this approximation factor gamma. It gets easier as gamma gets larger. That's all you need to know. So first, we should think about how one breaks lattice crypto. So the state of the art to break lattice crypto is to solve some gamma SVP instance, right? So in other words, like I showed you that scheme where we had some bad basis and Google had a good basis. And as far as we know, the best thing we know how to do to break that scheme is to find a good basis ourselves, which means to solve SVP. And I think this is philosophically interesting. Maybe I should have left this out. But the way that we solve this approximation problem is we reduce it to an exact problem in a low dimension. And kind of what I'm saying here is that SVP sort of has a self-relation with each other. Approximate SVP is closely related to exact SVP. Maybe I should have left this out. And a reminder that I'm not saying that we can break this stuff. Our best algorithms for SVP take 2 to the Cn time. So this is where we get the 2 to the Cn. This is where we get the best constants and things like this. We go through this chain. So these are sort of trivial reductions. Let me show you a non-trivial reduction. So remember, I showed you that lattice crypto, or I claimed that lattice crypto reduces to gamma SVP. It turns out that gamma SVP with some other approximation factor, which I'll call gamma sec for security, reduces to lattice crypto. In other words, if you can break lattice crypto with non-trivial probability, then you can solve gamma SVP. And this is called a worst case to average case reduction because lattice crypto is like a randomized problem, right? I sample my public key randomly in some way, or my secret key randomly in some way, and I hand you this like random lattice generated by it. But this says, but gamma SVP is a worst case problem. This says for any lattice, if you can break lattice-based crypto, you can find short vectors in that lattice. So this is something that makes lattice crypto really stand out. This kind of worst case to average case reduction is only known for lattice-based cryptography. Right? Like I said, the talk would have been essentially have been over a couple slides ago if I were talking about RSA here. But for lattices, we have this extra evidence. So let's just sort of rewind and see what we've got. So we have these 2 parameters now, gamma sec and gamma. And we know that gamma sec SVP reduces to lattice crypto, and lattice crypto reduces to gamma SVP. So in other words, breaking lattice crypto is essentially equivalent to solving approximate SVP. You know, if you squint, then that's entirely true. The only thing that's a little issue is that this gamma sec and this gamma are quite different values. But this is very compelling evidence for security. In particular, it's like far better than what we have for anything else. I should also say that the end of my talk, I'm going to be arguing against this stuff. So if you think I'm being too friendly to lattice crypto, I'll be unfriendly soon. We have another piece of evidence for lattice crypto, right? For the hardness of lattice crypto, and that's so now we know that SVP, that breaking lattice crypto is kind of equivalent to solving SVP, and we have proofs of hardness of SVP. In particular, if you know what an NP-hard problem is, like satisfiability or the traveling salesman or subset sum or something like this, we know how to reduce NP-hard problems to SVP for certain approximation factor, which I'll call gamma hard. Right? So for these approximation factors, if these problems, these NP-hard problems, which are very widely believed to be hard, are in fact hard, then SVP is hard too. And this is due to a long line of work. It was an open question for like 20 years to prove even for that exact SVP was NP hard. It was finally cracked by ITAI in 1998. And with a lot more work, we got hardness of approximation. There was a long line of work getting this gamma hard as large as possible. But we still, of course, have gamma hard much, much less than the other values that I showed, right? We want this gamma hard to be as large as possible. It's still not nearly as large as gamma sec or even gamma. So gamma, remember, is the approximation factor that we use to break lattice crypto. But what's cool about this is it means you don't need to know anything about lattices. You don't need to talk to someone like me to believe that solving gamma hard SVP is hard. You just need to believe some widely believed conjecture in complexity theory, and you need to know nothing else about lattices except that there's this reduction, and that's it. So that's quite reassuring, I think. So now here's the full picture. We know that lattice crypto up to some squinting is equivalent to solving gamma SVP, and gamma SVP is hard. So if you squint enough, you'll think that maybe solving lattice-based crypto is proven to be hard under reasonable conjectures, but because these gammas aren't exactly right, it's not there. But again, proving that problems are hard is hard, and this is what we have, and I think it's actually quite compelling evidence. So those are reasons to be excited about lattice crypto. By the way, if there are any questions, just interrupt me. Okay? Yeah.
So if gamma is constant, what's the best amount for solving gamma S?
Essentially, it depends if it's heuristic or not. It's like, okay, 2 to the n over 3-ish. For constant, but gamma's not a constant here. Gamma's always a polynomial, but that means nothing to you guys. So.
What's the exact value of C of the 2 to C, and what's the exact value of C?
So the best algorithms for exact or constant factor approximation are 3/2 to the n over 2. Maybe. Yes, I can. Yeah, so I think this is I'm on video. I shouldn't try to estimate constants. Okay, yeah. 0.292. So this is 2 to the 0.292n, according to Devesh, not me. Yeah. Cool. Any more questions? This is a very good time. I mean, I've heard this talk before, so it's very boring for me if I don't get it. All right, I'll be bored. So, okay, now I'm going to tell you about reasons to be worried about lattice-based crypto. Reasons why it might not be secure. And I should say, I work in this field. The reason I have a job is because people think this is secure. So I'm playing devil's advocate now. What I believe will be left as an exercise to the reader. So the first reason to be worried is from the slide I just showed you guys, right? So we have these really nice reductions. It's very surprising. It's very nice. It's more than we have for anything else. But these approximation factors, gamma, are different, right? So we could live in a world in which it just happen, in which gamma SVP is easy, but gamma hard SVP is hard. That's totally plausible. These are different numbers. In fact, we know of lots of examples of computational problems where there's just some sharp threshold. The problem's hard up to some point, and then you go a little bit above that point, and it becomes easy. We don't think that's true for gamma SVP, but we don't really have any evidence for that, besides the fact that we haven't broken these things yet, and the only way we know how to solve these things is to reduce to the exact version in lower dimensions, which sort of makes it feel like it's always the same problem no matter what the approximation factor is. But we could just be wrong about that, right? So the picture that we like to tell is we turn this knob as this gamma knob, and as gamma for small values of gamma, we can prove that it's hard. For larger values of gamma, we're in the range where we break cryptography, but we figure it's still hard. All we did is turn this knob a little bit, and for even larger values of gamma, we can prove that it's lattice-based crypto is as hard as that. But again, we just turned this knob a little bit. It's probably still hard. But that story could just be wrong. And just to mention, reasons why we might be nervous, the value of gamma sec, which I'm not going to tell you because it's meaningless to you. Well, it's n to the 1.5. Nobody has improved upon this for 15 years. since my advisor Oded Regev proved it originally in 2005. Maybe the reason we haven't improved upon this is because this is the right answer. Maybe it's the right answer because actually breaking lattice-based crypto is easy. And in fact, we know that there are fundamental barriers that prevent us from collapsing this sequence of inequalities. In fact, from getting anywhere close. These fundamental barriers are complexity theoretic. I don't need to go into them. Another reason to be worried is I keep using this word hard, and it would have been great if someone asked me what I mean by hard, because I didn't tell you. And the answer is complicated. And it's possible, in particular, that lattice crypto is hard to break, but not hard enough for practical applications. What I mean by that is that hardness results tell us something like no adversary running in time polynomial in the dimension can break our scheme as n goes to infinity. Right? And this is really interesting theoretically. I take n large enough, and this becomes a hard problem. But if I hand you an actual implementation, n is some fixed value, right? So what we actually want is for n equals, say, 1,000. These numbers shouldn't mean anything to you. No adversary running in time less than 2 to the 128 can break our scheme. That's what we want to say. And there's a huge gap between this kind of statement and this kind of statement. Right? This kind of statement is the kind of statement that complexity theory, that theoretical computer scientists are extremely comfortable with. This kind of statement, not so much. And so the question becomes, how do we even begin to do this? And there is an answer to this question, right? So the reason that this asymptotic, this kind of asymptotic result is so interesting is because it means just take n to be large enough, right? I mean, we've got pretty good computers now. Set n to be 1,000,000 or something. We'll still be able to compute it. And probably for 1,000,000, this is that hard. I mean, again, you guys don't know anything about numbers, but we think it's plausibly hard for 1,000. Probably for 1,000,000, it'll be hard. The problem is that if we want to base the internet on this, we really need to be careful about the parameters, right? If this is happening trillions of times, then it's very, very expensive to change from n equals 1,000 to n equals 2,000. So practitioners, just laugh at you. Like, the reason that lattice-based cryptography wasn't implemented, 10 years ago, like ideally it would have been, is because we didn't know how to make it efficient enough. We've now just sort of crossed, or a few years ago, we sort of crossed the threshold where practitioners were willing to implement these things at parameters where we think it's still secure. If we just double the parameter size to be careful, it's a no-go. We in fact do need these claims, like the claim from this last slide, this 2 to the 128, and that's what people make, right? So here are two schemes, A New Hope and Frodo, and in their papers they have these tables where they say set this parameter to this and that parameter to that, and we're 2 to the 255 secure or something. So we do in fact make these claims, in spite of the fact that theorists like me aren't very comfortable with such things. And how do they make these claims? Well, they assume that that our current fastest algorithms for breaking their schemes are the best possible. In other words, there will be no further algorithmic progress. And that's a little scary. I mean, for example, there's been a lot of recent algorithmic progress on these problems. This is not a dead field. I mean, this is a little disingenuous because these two results came out after these papers, but they didn't falsify the claims. But we're not done in this field yet. Or it's not clear that we're done. We don't understand this as well as we should. I don't think we understand this even as well as factoring. And factoring, we didn't understand that well. We've messed this up before. In particular, the original RSA implementation was broken in 1999. And it wasn't broken because, complexity theorists were wrong, because there was some polynomial time algorithm and our asymptotic results were false. It was broken because there was just a better exponential time algorithm. In other words, exactly the thing that I'm sort of worried about happened in this case. And for RSA, this wasn't a really big deal. This was not big news because well before the original implementation was broken, they'd switched to a more secure implementation with larger numbers. And that was okay back then. Because back then, people weren't, or I don't know when they switched, maybe the 80s or something, people weren't storing all internet traffic to decrypt it later. So it was okay that 25 years later someone broke those schemes because nobody wrote down the messages, as far as I know. But now we know that people are. So this is much scarier, right? We can't just say, oh, we found an attack, or we think there might be an attack coming soon, so we'll double the parameters, and that's fine. If we get it wrong now, people will read the messages that we write now. They'll read it in the future, but they'll still read it. I think at least, so we want these schemes to be secure, ideally forever, right? I mean, remember at the beginning of the talk, I said something about an adversary with a computer the size of the Earth can't solve this until the heat death of the universe or something like that. And those claims look a little less promising when I have to say, unless someone finds a faster algorithm, right? It's much less convincing. Maybe the heat death of the universe is farther away than the new algorithm. So maybe that's what we should be focused on. And I should say, not everyone believes this. Some people say, look, we find a faster algorithm, we'll double the parameters. But I think that's a little disingenuous. Especially the reason we're switching to post-quantum crypto in the first place is because we're worried about quantum computers being built. And what's going to come first, quantum computers or better lattice algorithms? Maybe there are no better lattice algorithms. So I showed you all this evidence previously to say that I thought lattice-based cryptography was secure. Right, I showed you this reduction from SVP to lattice-based crypto, and I showed you a reduction from an NP-hard problem to SVP. But actually, if you plug in the parameters that are relevant to cryptography, these reductions are useless. In particular, if you plug in all the numbers, you find that you reduce from a problem that I can solve on my laptop in both cases. It's not an easy problem for my laptop, but it's doable. So both of these are actually don't tell us anything about quantitative parameters at all, which is rather disappointing. So we can still take them as evidence if we want to say, well, we can prove some kind of hardness. That probably what's actually true is a stronger version of hardness, but it's no longer as strong a case as I originally claimed. So now is again an excellent time for questions if anyone has. Again, I'm just really bored up here, so okay. So in the final act, I'll talk a little bit about work I've been doing with Devesh and others, in which we take little tiny steps to proving security. Again, we can't prove security. That seems way out of reach, but I'm trying to make a stronger case for secure lattice-based crypto. I mean, I'm also trying to break it, but this seems more promising. So remember before I had this idea of a reduction. That's really how we give evidence of hardness. We reduce problem A to problem B. And I just sort of said blithely, again, I use these words hard, and I said, oh, if we can solve B efficiently, then we can solve A efficiently. And I didn't tell you what those words mean. So there's sort of a trend in complexity theory now to do what's known as fine-grained reductions. In fine-grained reductions, we're really careful about what we mean by efficient, what we mean by hard. So we say, A with input size n reduces to B with input size 2n. Therefore, if A is 2 to the n hard, then B is 2 to the n over 2 hard. Right? Does that kind of statement make sense? So this is kind of a new big trend in computer science. And we're trying to apply this stuff to lattices because, these are the kind of statements that we want. We want 2 to the n over 2. We don't want no polynomial time. So we have a couple results in that vein. In particular, for some non-explicit constant epsilon in joint work with Huck Bennett, Sasha Golovnev, and then another joint work with Devesh, we show that there's no 2 to the epsilon n time algorithm for SVP. This is for exact SVP. Epsilon's really low, but proving lower bounds is hard. So we're pretty happy about this result. And of course, this is not unconditional. This is assuming a conjecture about the hardness of another problem, in particular gap 3 sat, if you know what that means. And this result, it's not actually just for exact SVP. It even holds for small approximation factors. They're constant. We're proud of that, but that doesn't mean anything to you. So we're kind of on our way. Right, so I showed you before, like there's this long sequence of works proving better and better hardness results for SVP, where there all they meant is, by better was no polynomial time algorithm, and they got the approximation factor larger and larger and larger. Here we're trying to recreate that, but now fine-grained. And it's much, much harder. If you remember, I told you that it took like 20 years to prove that SVP was NP-hard. Right? They didn't have these fine-grained restrictions. Now we're trying to do it with these fine-grained restrictions, and it's hard. But we're doing it. We also have very strong hardness results for closely related problems, including these that aren't even up yet. We have tight bounds for problems in coding theory. That's joint work with my supervisor at MIT, Vinod Vaikunthanathan. We also have essentially tight lower bounds for the closest vector problem, which is a slight variant of the shortest vector problem that's known to be harder. So that we think of as pretty strong evidence. And with Devesh, we have very strong lower bounds for SVP, just not in the right norm. The Euclidean norm is, our favorite norm. We live in it. But we have this for LP norms, for norms that we like less. So, because this is my talk and I get to say what I want, here's my dream. What I would absolutely love to do is do the following. I'd like to reduce a hard problem in a fine-grained way to SVP. This is already kind of done. I'd like to improve the parameters, but I'm pretty happy. And then I'd like to go up the chain. I'd like to reduce SVP in a lower dimension to approximate SVP in a higher dimension. Then I'd like to reduce the exact right gamma SVP to lattice crypto. I'd like to just go up this chain, show that every step in this, in other words, show that every step in this, well, there are only 2 steps here, but there should be a longer chain if I were being more exact. I want to show that all these steps are tight. In other words, the best way to solve gamma SVP is the way that we know how to do it. The best way to solve lattice crypto is the way that we know how to do it. And that's provably true because the problems are equivalent. So this is my dream goal. It's not going to happen, but I'm still going to try. So that's essentially my talk. I'll just summarize what I've said. So maybe the most important thing to get out of this talk is send embarrassing emails, but the lattice crypto is coming. This is going to happen. And the reason it's going to happen is because of quantum computers. In particular, I think there are people in this audience who work on quantum computers, and this is probably something you should be aware of just for that reason. And before it comes, I'd really like to understand the security as well as possible before we bet the security of the internet on it, right? Before, not after. And we have very strong evidence for asymptotic security. I'm not sure how much you guys bought that, but at least to me, we have very compelling evidence. I don't think there's a polynomial time algorithm that breaks lattice crypto. My advisor once asked me, I'd written up a sloppy proof, and he asked me, would you bet your PhD that this is correct? And I would bet my PhD that there's no polynomial time algorithm for lattice-based crypto. And because we have this strong evidence, we have these worst case to average case reductions, we have hardness of the shortest vector problem, even the approximate form, but we have much less evidence for quantitative security. I mean, I'm fairly confident that the quantitative security claims that people make are right, but I'm not betting my PhD on it. I like my PhD. So right now, all we have is some fine-grained hardness results. They tell us something. They really suggest that lattice crypto is pretty hard, but nowhere near hard enough to satisfy the practitioners. And so what we're doing right now, what I'm doing right now, and Devesh is doing right now, is trying to prove as much as we can as fast as we can, because we'd like to understand this as well as we can, again, before we bet the security of the internet on it. Well, I should say, the evidence that we have for the security of lattice-based cryptography is still better than the evidence that we have for the security of anything else. We've already bet the internet on other things. So the only reason I'm freaked out about this is because suddenly this is in my territory, so I don't want it to be wrong. Anyway, that's my talk. Thank you.